Welcome to my presentation. This is a presentation. I will show you now the results of a joint investigation we did with two different partners. One company is Ceratizid from Luxembourg, which is a manufacturer of cemented carbides, and then the other company is AKE, also from Germany, a producer of saw blades. A saw blade is a steel blade which has many cemented carbide tips, which has to be brazed on, and there are different kind of brazing filler metals used to do the brazing job. This can be normal brazing filler metals, but also some special brazing alloys which can be seen here, and I'm not sure how that one is working. Here, okay. Here you can see the steel blade, and here the cemented carbide tip, and there here in between is the brazing filler metal, and this is a special brazing filler metal. You can see some red color, some copper in between. These brazing filler metals are called sandwich brazing alloys, and they consist of three different layers. So there's a normal brazing alloy layer, which makes the connection to the steel. There is an intermediate layer of pure copper or a copper alloy, and again another brazing alloy layer on top, which makes the brazing joint to the cemented carbide. What is the reason for using these special sandwich brazing alloys? The reason is the different thermal coefficient of cemented carbide and steel. This does not have any effect during brazing, but after brazing. When the part is cooling down, this can result into stresses. And the cemented carbide tips, this is a brittle material, and they don't like tensile stresses. This can lead to failures, and the job of this copper layer in between, because it's very ductile, it will take over these stresses and protect the tip for cracking. But beside this, products on the market which can protect the saw tips, there we can see in the industrial field still some failures, and here, for example, here you can see there is an uneven and inhomogeneous copper layer in between. These kind of failures had been investigated some years ago by our colleagues Magin and Rasbach, and the results of this finite element analysis was presented 2009 in the Brazing seminar. And there you can see here the optimum, when you have very continuous copper layer in between the cemented carbide and the steel. Then you can see different failures, and in the last one you can see the brazing alloy without any copper layer in between. And the bottom side you see what happens on the cemented carbide tip, especially on the surface, and you can see the influence of the sandwich brazing alloy directly when you compare it with a normal brazing alloy. There you can see the tensile stresses on the top surface of the cemented carbide, and here you can compare it with the sandwich brazing alloy, and there you can see how it works. After that presentation, we did an ongoing work. We present the influence, or what is the optimum foil width a customer should use to get the best results after brazing to protect his cemented carbide tips, and that was a result we found during that time. But there's still an ongoing question from our customers they ask us, what is the optimum brazing gap width when we braze cemented carbide, when we braze the saw blades? And this is what we try to do during this investigation, and we did different things. We did practical things and finite element calculations. Based on our experience with the other presentations and investigations we made in the past, we decided not to use a real part, and we decided to use a different kind of specimen, and we decided to use a 4-point bending test. And we had 2 cylinders of cemented carbide with a 10% of cobalt binder, and here is steel. And in between, the different kind of brazing filler metals were placed. we used these three different kind of brazing metals, brazing alloys. One was the normal brazing alloy, HD.mp4 according the ISO standard, or BH22 according the AWS. And later on it will always be called BFM449 when you want to follow. And two different kind of sandwich brazing alloys. One is a normal sandwich brazing alloy with pure copper inside, and the other one is with a modified layer in between. The colleagues of AKA, they made the brazing tests and in between they used different kind of brazing filler metals with a diameter of 6 millimeter and a thickness of 0.4 millimeter. Used a flux which was applied on both sides, and this brazing temperature was set and the brazing time was set to 2 seconds. They had a special fixture which allows to set the brazing gap afterwards. So the part was pressed to a final gap which we want to reach afterwards, because we want to create different gap sizes and to see how the result is. After the brazing, we had a centerless grinding process to get, we grind down to 4.0 millimeters diameter of the parts. After these parts were brazed and grinded, we make the 4-point bending test. Here you can see how the test specimen was placed in between. It was used as SWIC testing equipment, and the speed was 1 millimeter per minute. And we stopped the test after the part broke, or after we get a drop of 10% of the maximum force we applied to the part. Here I show you a short video. First of the normal brazing filler metal. And very often it broke. Now we go back to the other one. Not so easy. And now we have the sample with the sandwich brazing alloy in between. Is it running? Yeah. As you can see, it's not that spectacular as the other one, but there you can see what how the copper interlayer works. It protects really the part, and it takes up the stresses, and it makes a plastic deformation. So let's go back. So, besides the practical things, we also made finite element analysis and built up a model. But we made only a half model, and afterwards we doubled it for the calculations. And when we get closer to the joint area, the net was set much finer than at the ends. And here you can see the net for the sandwich brazing alloy, where you have the two brazing alloy layers and the copper in between. And what we did was a two-step calculation. First, we made the calculations after brazing and have a look what the stresses are in the parts at that side. And then afterwards, we applied different loads to the part and had a look what happens onto the part. Also here a short video to see, but I will only show you the one. And there you can see how the simulation works, and it's quite interesting. On the top side, the copper in this simulation or the brazing alloy was pressed out, and on the bottom side it was sucked in. So now we come to the results. First we look for the results for the normal brazing filler metal without any sandwich in between. And these are the results on here on the x-axis. We have the different gap sizes we found out after the tests. And here the maximum force we applied onto the part. What we can see also, we try to have a look to investigate where we get the failure And when we had very small gap sizes, the failure was mainly very close onto the steel side. And then we can see an area with higher values where we could not detect any which failed below 1,500 Newton. And then again, the force decreases, and there we get a lot of failures very close in the interface to the cemented carbide. And we could say that it seems to be an area where we had the highest values, and these seems to be around 100 microns. Besides that one, we also made this finite element simulation, and this is now here the result for the tensile stresses. It was too slow. There you can see here the effects, and I ask you to remember the colors when I show you the other video for the sandwich brazing alloys. And now look in detail to the results. On the x-axis, we have the different gap sizes, gap thicknesses. And the dark green color is first we are looking now for the maximum tensile stresses in the cemented carbide. This is where we're looking now. After brazing, there's not a big difference in between. But then when we add in the simulation load to the part, we can see something that the stresses in the cemented carbide decrease at again 100 microns, and then slightly increase again. Now we have a look into the mesostresses inside now the brazing alloy layer, and then we can see that we have here higher, or a little bit more green color, higher stresses at the 50 microns, then at the thicker layer decreasing, and then when it's getting bigger again, it's increasing. And this would also correspond then to what we found in the bending test, that when we had thin layers, we found a lot of cracks close to the steel, where the brazing alloy has to force the stresses coming from the steel. Then there we have a medium area, and then again, when it's getting very thick, the alloy also has different thermal coefficient than the cemented carbide, and also there it creates some higher values, some higher stresses inside. When we now look to the mesostresses in the brazing alloy layer, this is quite interesting. After brazing, we can see that the stresses in the thin layers are very high, and then they are decreasing. And this is similar to what we found when we have the small layers. We could see that the failure was mainly on the steel side. And then we add the load, and then again, we could see that the stresses inside the brazing alloy layer, we had a minimum again around 100 microns. And this is similar to our 4-point bending tests. Now we'll have a look for the sandwich brazing alloys. And there it looks like this. Again, here the brazing thickness, and here the force. And what we can see is more clouds than any tendency. But what we can see, there's a difference in between the brazing alloys. So one is the normal pure copper, and we use the 94 Cu+, which has a modified copper layer with a higher strength. And this higher strength, which we can see in our shear test, we can also see here now in the 4-point bending, that the average strength of the parts brazed with a Cu+ is approximately 25% higher than with the other one. But for the gap size, we cannot see any big influence. So these are now the results for the parts. Now we have a look for the video. When you now compare the colors against the normal brazing alloy, you can see it's less gray, less red, so you can see how the copper interlayer works and protects the cemented carbide. When we now look for the results, we found something different. We're now looking for the maximum tensile strengths in the cemented carbide. And as you can see, you cannot see big things to explain you here how the calculation was done. The interlayer was always set to 200 microns, and we changed always the brazing alloy layer. As you can see here, it was always increased. But the size of the gap does not have any effect to the stresses in the cemented carbide. When we look also now into the brazing alloy layer of the sandwich brazing alloys, we can also see only slightly differences. And we look now also here for the mesostresses in total. We can see the same tendency for the brazing alloy layer after brazing, but when we put on the load, there's no big difference here from 50 microns to 100 microns, only then is an increasing to when we reach the 150 microns. Now let's come to the final conclusions. First of all, it was very nice to see that the practical tests and the simulations showed up the same results and same tendencies could be found. When we look now for the normal brazing filler metal without anything in between, we found in our 4-point bending test that we had the highest values at a gap size of 100 microns. And when we look for the stresses, we found a minimum also again at the 100 microns. And therefore, the recommendation is for customers using pure brazing alloy. A gap of 100 microns seems to be the optimum in brazing in the tooling industry, which is very often also could be observed in good parts. What are the results for the sandwich brazing alloy? There we could not find a big influence of the gap size, but we could find a difference of the sandwich alloy composition in between. And the results here, what we found in the real tests, could be again found in the simulation. So that we can say for the sandwich brazing alloy, there is not a big influence of the gap size. The strength of the final part depends mainly on the composition of the interlayer which is used. And yeah, these findings of the investigation will help us and to give recommendations to the customers and helps us also in developing new brazing alloys. And then thank you for your attention.